All right, Pre-Cal 12, here we go. Video number 4. As promised, we are going to now look at infinite geometric series. So these are series that continue infinitely. So you would think if something continues infinitely, then it must go on forever. But no, what we get is we get something called convergence or divergence. So either your series converges to a point or it diverges to infinity. So consider these two scenarios. So the first scenario is imagine you're standing a foot away from the wall and you always move half the distance to the wall. So that is given by this here, right? We go 1 and then we're half a foot away and then we're quarter of a foot away, we're 16th and we're 32nd. That number is never going to get to 0. It's not going to happen. Your denominator is going to get infinitely large, but it's never going to be a 0 in the numerator. So eventually you'll get to a point where you're, like 1/1 billionth of a foot away from the wall. So for all intents and purposes, what do we say? We say you're at the wall. And that's the thing. That's why we say there's the point of convergence. Because if we plug this, if we just, we're gonna number crunch these things eventually. But what this does is this actually kind of gives you sort of a precursor to calculus, where you say the limit as x or n goes to infinity, because we have this equation essentially, right, for our pattern, that as n gets infinitely large, we end up with 1 over an infinitely large number, which we say is 0, because 1 divided by an infinitely large number gives us an absolutely tiny number, so close that we say it's 0. So that is an example of convergence, and we get that whenever our ratio is a proper fraction. If our ratio is in between -1 and +1, you are going to converge. If it is not in between -1 and +1, and you can see here, just speaking of the ratio, right, we have 1/2 divided by 1, which is a half. We have 1/4 divided by a half, which means we have 1/4 times 2, which is again 1/2. So we have a ratio of a half. If you ever get a ratio of a proper fraction, your sequence will converge. Now, if you have a ratio that is bigger, you are going to do what's called diverging, because you're going to diverge away from a given value and you're going to end up at infinity. So in this case, when your R value is greater than 1 or greater than, well, less than -1, which just means a bigger negative number. Because look at this pattern. We're now multiplying by 2. And as n gets infinitely large, now we end up with 2 to the power of infinity, which is 2 to a massive number, which is going to give us a massive number. So we're diverging. We don't converge to a point, we diverge infinitely large. So that's the difference, and it all comes down to your ratio. Now, what we get for a geometric sequence is we can sum an infinite geometric sequence is we can sum it up, and we get a very simple equation. It's just this. Sn is equal to a over 1 minus r. But it's really important that our r value is, in fact, between 1 or -1. Because if it isn't, then we cannot calculate this, and we do not get a sum. Because if we're diverging, there's nothing we can add to. Our sum eventually goes to infinity, so we get an unsummable value. So you need to calculate your r value first before you can even consider the sum of a series. So let's look at this series. We got T1 is 2/5, and T2 is -4 over 25. So to find R, it's -4 over 25 divided by 2 over 5, which means we have -4 over 25 times 5 over 2, which simplifies to 2 over 5, -2 over 5. So that's our R value. So our R is, in fact, a proper fraction. So we know we're going to converge. We're going to have a finite sum. So then we just plug this in. So in this case, n is infinity. That's why we don't need n in our equation, because we're an infinite series. My a value is 2 over 5. And my r value is -2 over 5. So you get 2 over 5 divided by 1 plus 2 over 5, which is 7/5, or 1 2/5. And then crunch that in our calculator, we get 2 over 5 times 5 over 7. And what do we get? We get 2 over 7. So we will actually, our total will converge to 2/7, because the number gets so infinitely small that we're adding that we just say we converge at 2/7. There's a funny joke, actually. Well, funny if you like math. A joke to explain this sequence, and the joke is two people walk into a bar, and the first guy orders one drink, and the second guy orders one half. And then the third guy walks in and orders 1/4. And then the fourth guy walks in and orders 1/8. And what you get is you get a sequence where the denominator is getting infinitely large. So every person that comes in gets smaller and smaller amount. And the joke goes, and then the bartender just says, you guys are all idiots, and pours 2 drinks because this part of your series will converge to 1. So we end up having 2 beverages. So, and I hope I didn't screw that joke up. I'll have to Google it to find out. So just like our other notation, we have sigma notation for infinite series. The only difference in our sigma notation here is that n is infinity, right? Because we are not going to have an n value because we have an infinite series. So how do we determine information from here? Well, in this case, find the sum of this series. So in order to get that, remember, we are going to use our S infinity is a over 1 minus r. Now, we need to know what our a value is. We know what our r value is. This is our r value here. This is what's changing. So r is equal to -1/2. So what's our a value? Where our a value, be careful here, k starts at 2. So our a value occurs when k is 2. So let's compute that. We would have 8 times -1/2 to the power of 2 minus 1, which gives us 8 times -1/2. So we get -4. So a is -4, and now we have info to use our summing of an infinite series equation. So -4 over 1 minus -1/2, which means -4 over 3/2, which is -8 over 3. So that is the sum of this infinite series. So again, sigma notation just simplifies, changes your expression for a summing of a pattern, and it does it in a lovely, scary sigma notation. So that is how we can solve an infinite series. There's not much wiggle room here because either it converges or it does not. If it does not converge, we cannot solve. If it converges, it's a relatively straight calculation. But what about everybody's favorite, word problems? How do we do a word problem with an infinite series? Well, we just assume an infinite swing. So this pendulum is going to stop. But if you think about all of the minute swings, right, before it has such minute little swings that we say in the end it stops, right? It's similar to walking to the wall. We're just like, okay, it's going to stop. Because if it lessens its swing by 5%, there's no way you'll ever get to 0 because you can keep taking 5% of a smaller and smaller number. So eventually we say, okay, it stopped, it's at 0. It converges at 0. So what information do we have? Well, we know the length of our swing is 25 centimeters. That's our first swing. And now R, though, is 5%. But what does that mean? Okay, that means it swings, lessens by 5%, which means if we had a 100% swing, every swing it drops 5%. So R is not 0.05 or 5%, R is 95% because that is how much remains after each swing. So we have an R value of 0.95. And from there, we're done. We use our equation. Sum of this series is equal to A over 1 minus R, which gives us 25 over 0.05, and we get 500 centimeters. So again, since this series converges to 0, we then say it stops. And obviously a swing will stop, but the mathematics of it saying it only lessens by 5% will technically never allow us to get to 0. So with the converging at 0, then we say, okay, this thing definitely stops, and we can calculate it as an infinite series. Let's do one more here. So you have a ball. Well, we're going to do more than one, but here's one more we're going to start with. You have a ball, and you drop it from 12 feet, okay? Now again, if it only ever rebounds 2/3 of the distance, then mathematically speaking, you're never going to get to 0 because 2/3 of a number will always give you another number, even if you get to 2/3 of a tiny amount. But obviously that ball is going to stop, which is why we say again, this pattern converges at 0. So we have a ball and it's dropped from 12 feet. So visually, what does that look like? Here's your ball and it's dropped from 12 feet. And then it bounces back up and it bounces back up 2/3 of the way. So what does this look like? Well, our A value in this case is not 12, okay? Our A value is going to be 24 because if we're considering the full bounce, right, then we need to consider because if we're dropping it from the top, we need to actually consider what a full bounce cycle would have looked like because our bounce cycle looks like this. So if we're considering a full bounce cycle, it starts at the bottom and then ends at the bottom. So we need to consider this other value, which is 12 feet. So what we do is we add that together and we say, okay, A is 24 and R is 66%, 2/3 of the distance. But what we do with this is we take the sum value, but then we have to subtract this additional 12 feet of vertical distance that we have incorporated at the beginning of our equation. So we take out that initial up value, and that just allows us to reconcile that additional scenario. So we fill this in now. From here, it becomes, again, pretty easy. A is 24 minus, or over 1 minus 2/3. So we get 24 over 1/3, which is 24 times 3. So that gives us a total value of 72, but then remember we need to subtract our initial 12. So we get a total vertical distance traveled of 60 feet. This is a pretty common example you see in a lot of books, and it incorporates this. You could also solve this from peak to peak here, but then there's another little additional calculation you need to make. This is a much easier way to consider it. Consider every bounce cycle, and then just subtract that initial 12 feet for starting at the bottom. All right, now consider repeating decimals. All right, if you think about a repeating decimal, it's a number like this: 0.2 and then 4, 4, 4, 4, 4, 4. And remember that this was a note from grade 9, every fraction can be written as a terminating or repeating decimal, which means we can actually represent this as the sum of a whole bunch of fractions, because this answer is a fraction. So think about your value. This is your placeholder system, right? This is your tenths. So we start with 0.24 repeating gives us 2/10. And then we have 4 100ths. And then what do we have? We have 4, but in the 1,000th position. And then 4 in the 10,000th. And that 4 is what continues. So this initial 2 is not part of our repeat. This is our repeat here. So what is happening to our repeat? Well, 4 over 1,000 divided by 4 over 100 is the same as saying 4 over 1,000 times 100 over 4, which gives us 1 over 10. That is our R value for this repeating chunk of our decimal. So if we're going to sum these things up, right, because that's what we want, we're going to get the value of the fraction if we sum up all of the fractions. We start by taking this piece, because we're going to need that, and then we add it to the sum of the rest. We add it to this. So the infinite sum of, let me make that look a little nicer, A, which in this case is now 4 over 100, because that's our next term, right? That's where our A actually starts in our pattern, over 1 minus 1/10. So 4 over 100 over 9/10, which we can simplify a bunch of this, right? 4 over 100 is just 2 over 10, which is 1 over 5, but 2 over 10 and then 10 over 9, because we flip and multiply, and we end up with a sum of 2 over 9. So the sum of this whole repeating 4 business is 2 over 9. So we add that to our initial 2/10, and what do we get from there? We get 11 over 45. That is the sum of the entire pattern represented here, which is the value of 0.2444444. And if you were to take 11 and divide it by 45, that is where you're going to end up. And there's some pretty interesting mathematics that breaks down into that. If you take some number theory in university, you end up with proofs and formulas as to how many decimal or how many numbers occur after the decimal, what the pattern is. It's pretty interesting. And this is just an example of how we can use fraction notation and summing in order to get a full fraction value of a repeating decimal. So you could do the same with a terminating decimal, obviously, but you wouldn't have the repetition. So you wouldn't have to do the infinite sum portion. This is how you can do it with a repeating decimal that goes on infinitely. So that is infinite sequence or infinite geometric series. I hope it makes relative sense. You can always watch it again and always practice the workbooks found on my website at mrherlar.weebly.com and move forward from there. Section 2 in my course dives now into transformations of functions and other operations with functions, inverses, and arithmetic combinations. It's a pretty good time, and it's a kind of an opposite concept. There isn't a lot of progression from section 1 to section 2, and after there we continue to grow. So I hope this one worked out for you. On to something different and equally exciting. All right, have a lovely rest of whatever you're doing, day, night, and I will see you next time.